In this video, we'll learn how to apply seismic load in SAP 2000. So the situation is we have to define seismic load for South Carolina, United States. The site class is site class B. Importance factor is 1. We have a dual system, shear wall and special moment reducing frame, and risk category 2. We have to use ASC 710 for application of load, or you can use ASC 716. Very similar load defined criteria. So this is the table. We have to select the value of strength, response factor and deflection criteria. And let's go to SAP 2000 and define the load pattern for the seismic. So this is the model we have modeled in lecture 24, and I'll be utilizing the same model. So you are very familiar with this model. So let's go to, we can also see the model in detail in three-dimensional view. So you are familiar with this model. We have worked on this model in lecture 24. First, start with defining the load patterns. We have already applied other loads to this same structure, the gravitational loads. Let's go to earthquake in X direction. In latest SAP, we have the load case defined as quake, but in previous SAP version we have the load of the earthquake defined as seismic. So it is it's just difference of the name. So we'll select the quake option from here and select our loading code for the lateral load criteria. We have the loading code available as ASCE 716 here. The criteria for 716 and 710 is very similar, so I'll be using the 716 here because ASC 710 is not available in this version. So we'll be using parameters from 710, ASC 710. Now click on modify load pattern. We have to apply in global X direction. The diaphragm eccentricity applies for the torsion in the building, for inducing torsion in the building. Due to the lateral load, the code recommends taking a 5% eccentricity for the earthquake loads. Similarly, for 0.2 second spectral acceleration or short-term spectral acceleration, we'll go to the code part where we have given the maps. So this is the South Carolina. This is the location we are to apply the structural loads as risk adjusted maximum considered earthquake, and this is short term acceleration. The value is 150, and since it is in percentage, so I'll be assigning it as 1.5. sorry. Similarly, for S1, the S1 graph or the spectral acceleration for 1 second period is given on the next page. We'll be using the same location as given in the situation, and see the location on the map. On the contour plane we have value as 60 or 0.6. So it's South Carolina, and the site class is also B as given in the map. We have site class B. So it is in percentage of G, so we'll be using 0.6 since it is in percentage. So divide by 100 becomes 0.6. And site class already selected as B. Now we need to see the long-term transition period, the T value, and it is 8 seconds for here. It identifies the extent of the spectrum, you can say. Now the response modification factor for our structure consisting of special reinforced concrete shear wall is 7, and over strength factor 2.5, and amplification of deflection is 5.5. Importance factor based on occupancy, considering it is a residential building, we can say that it is 1. Importance factor given already as 1. If your building is a hospital or any emergency communication tower, then you have to see the code for other cases. But right now we need to learn how to specify the importance factor in the SAP 2000. Anyways, for the time period of the structure, we have the CT value and X value from the code. This is table 12.8-2 ASCE 710. So for all other structures, since it is a dual system, not a moment resisting frame, so we have selected the appropriate value. And now we have to select the risk category and the seismic design category. So it based on SDS value, the seismic design category is class D, and based on the value of SD1, your seismic design category is class D as well. Sometimes it happens that based on different risk categories, seismic design categories become different, but conservatively we take the higher one. For example, your SD1 would have identified the structure as seismic design category D, or SDS would have identified it as seismic design category C, but conservatively we'll take it as D, comparing both. So I have defined the same load case for EY as well, only the change was direction, that was specified as Y. Now we have to specify the seismic design category. But please note that in Y direction we have a special moment frame, not shear wall. Shear wall is not acting as a part of frame, or you can say as part of lateral force resisting system. So we have added all the values for the moment frame only. So this is very important to learn. For moment frame our value is 0.28, 0.028 and 0.8. And how it is moment frame in Y direction, it can clearly be seen. This is my Y direction, and the shear wall is not resisting the forces in Y direction. It is perpendicular to the Y direction, that is X direction, for which we have considered the structure as dual system. But in Y direction it is only moment resisting system that is resisting the lateral load. So now we are defining the mass source for earthquake. This is where the dead load of the structure would be coming from, as well as 20% live load as per ASCE 710. You can search the code for the references, but right now our concern is defining the mass source in SAP 2000. Right now I'm adding all the dead loads as well as 20% of the live loads, adding 20% of the roof live load as well. So we have added all the gravitational loads for the earthquake base shear calculation. So sometimes we have to specify the building height for calculating the seismic base shear, but in latest SAP version which we are using, it has the option to consider the building story height automatically, the building total height automatically. The lateral load elevation range over here we have user specified, which is already considered as correctly. So you can also either take program calculator or manually specify the total height of the structure from which point to which point the base shear has to be applied. Now let's assign the seismic design category, which we go to steel frame design, and it is already assigned as seismic design category D as per our values of SDS. You can change it to effective order analysis, and you can see the details of this part of analysis in the theoretical part, but this is how we change the effective order analysis. Usually it is appropriate to do effective order analysis for single story or double story or smaller structures. Similarly, we are to define the diaphragm now. Now, in order to assign diaphragm to the structure, we have to select the floor, especially the edge joints, assign constraints. And since it is a 6-inch thick concrete slab, we have to assign a rigid diaphragm. So I'm saying, since this is the roof, so I'll name it as roof, and constraint axis in Z axis, and click on OK, and click on OK, and now apply. So it has applied the diaphragm. Diaphragm distributes the lateral forces to the vertical members from the slab. Similarly, I'll go to the lower level, that is the floor level, and then assign the diaphragm from here. Assign joint constraints, define joint constraint, select diaphragm from here, and click on add new constraint. Click on floor 1 and click on OK, then OK, select it and click on OK. Now we have applied the lateral load to the structure, including the diaphragm, which will help the software to distribute the lateral forces.